At 2 in the morning, you ask an AI to rewrite one awkward email. You press enter. A few seconds later, the answer appears. No smoke. No spinning turbine. No water pipe running through your desk. The whole exchange feels almost weightless, as if your question floated into a cloud and came back carrying better punctuation. But the cloud is a metaphor. Your words travel through networks to a real building. Inside that building, specialized chips pull electricity through power equipment, turn most of it into heat, and ask a cooling system to carry that heat away. Outside, substations, transmission lines, and power plants have to be ready before you press the button. So is one harmless email secretly draining a reservoir and raising your electric bill? Not exactly. That is the first surprise. A short text prompt can be individually small. The physical problem appears when tiny requests become billions of requests, when larger models generate images, video, and long reasoning traces, and when entire facilities must remain ready for the busiest minute of the day. The real question is not, how guilty should I feel about one prompt? It is, what system are we building to make AI feel weightless? And who carries the weight when it is finished? Imagine following your sentence after it leaves the screen. It does not fly directly to one magical GPU. A production service may route and classify the request. The model reads your input, then generates the answer token by token. Accelerators do much of the mathematics, but host processors and memory support them. Other machines sit partly idle so the service can survive sudden traffic. Power conversion equipment keeps the electricity stable. Network gear moves data. Cooling equipment removes heat. Google published one unusually detailed measurement of this full stack. For the median text prompt sent to Gemini apps in May 2025, it reported 0.24 watt-hours of electricity and 0.26 milliliters of water. That electricity is less than an LED bulb uses in a few minutes. The water is a few drops. But this is not the number for AI. It describes one product, 1 month, one median text workload, and one accounting boundary. It excludes training, long-term data storage, your device, and the external network. A long reasoning task, an agent using tools, an image, and a generated video are physically different jobs. OpenAI's chief executive has cited 0.34 watt-hours for an average ChatGPT query. But OpenAI has not published enough of the measurement boundary to make a clean comparison. This is why viral arithmetic becomes dangerous. People take the maximum power printed on a chip, multiply it by a guessed duration, then announce the cost of a prompt. But a server batches requests, utilization changes, and the chip is only part of the system. There is no honest universal number for one AI request. And yet the absence of one magic number does not make the physical system disappear. For years, data centers became more useful without demanding dramatically more electricity. Servers improved. Work shifted into efficient hyperscale facilities. Companies packed more computing into every unit of energy. Then accelerated AI servers began changing the curve. Berkeley Lab estimated that American data centers used about 176 terawatt-hours in 2023, roughly 4.4% of all U.S. electricity. Its newest update places the 2030 reference case at 649 terawatt-hours, or 11.8% of U.S. electricity. That is a forecast, not a meter reading from the future. The report's wider range runs from 521 to 843 terawatt-hours, depending on chip shipments, utilization, equipment life, and cooling performance. The uncertainty is enormous. So is the direction of travel. FERC staff estimated that more than 50 gigawatts of data center capacity was already in service by the end of 2025. The average new facility entering service in 2025 was more than 3 times the size of one entering service in 2020. Why does AI change the shape of the building? Because powerful accelerators can be packed into dense racks. Training can concentrate thousands of chips on one model. Inference repeats whenever people use the finished system. And low-latency products keep spare capacity available because nobody wants a chatbot that says, "Please return after dinner." One prompt may be small. A promise of instant access for hundreds of millions of users is not. Now the story leaves the server room. A data center can be planned and built faster than a major transmission line or power plant can be approved, connected, and completed. The computer industry moves on product cycles. The grid moves through engineering studies, permits, equipment orders, land negotiations, and public review. America does not lack proposed power projects. At the end of 2025, more than 2 terawatts of generation and storage were waiting in interconnection queues. But a queue is not a power plant. Among projects that actually began operating in 2025, the median journey from interconnection request to commercial operation exceeded 5 years. Many proposed projects never reached the finish line at all. Meanwhile, North American grid planners expect summer peak demand to rise by more than 224 gigawatts over 10 years, with new data centers accounting for much of the projected growth. This does not mean AI will consume the whole grid. It means the pressure can become intense in particular places. Data centers cluster where fiber, land, tax incentives, and power are available. A load that looks modest on a national chart can dominate one utility's construction plan. The grid must be designed for location and peak demand, not for a national average. That is why two statements can both be true. Globally, data centers remain a minority of electricity use. Locally, one new campus can be among the largest loads a utility has ever tried to connect. The cloud has a street address. Every calculation ends as heat. That heat has to move from chips to coolant or air to the building and finally into the outside world. Some facilities use chilled water loops and cooling towers that evaporate water. Others use air cooling, dry cooling, closed liquid loops, or combinations that change with climate and workload. Berkeley Lab estimated that U.S. data centers consumed about 66 billion liters of water on site in 2023. The electricity supplying those facilities carried a much larger indirect water footprint, nearly 800 billion liters, because many power plants also use water. Those are national model estimates. They are not a water meter attached to ChatGPT. The famous claim that a bottle of water buys only a few dozen AI answers came from a modeled GPT-3 scenario. It was not a direct measurement of today's ChatGPT. Location, weather, cooling design, power source, model, and answer length can change the result dramatically. And technology can change the trade-off. Microsoft says its newer closed-loop design can circulate the same coolant without continuously evaporating fresh water for cooling. That does not create a water-free data center. The building still has ordinary water uses. Its electricity may carry an indirect water footprint, and older facilities use different systems. But it proves an important point. Resource use is not a law of nature attached to the word AI. It is partly a design choice. The honest question is not, how thirsty is AI? It is, which system, in which place, using which water and power technology. Suppose a utility expects a giant data center. It may need a substation, transmission upgrades, and new generation years before the facility reaches full size. If the customer arrives and uses the power, those assets can serve a large, steady load. But what if the project is delayed, downsized, or canceled after the grid has already been built? The steel remains. The debt remains. Someone must pay. This is the part hidden by arguments about the cost of one prompt. Your bill is shaped less by a few drops of cooling water than by decisions about billions of dollars in long-lived infrastructure. Virginia's legislative watchdog modeled what that could mean in one especially exposed region. By 2040, the added generation and transmission cost associated with data center demand could add roughly $14 to $37 per month for a typical Dominion household, measured in 2024 dollars. That is not a current bill increase. It is not a national forecast. And the same report did not find that data centers had historically escaped their current cost of service. The warning concerns the next grid and the risk of building for demand that may not arrive as promised. In PJM, the independent market monitor estimated that data center demand accounted for about 3/4 of the increase in capacity market revenue in the 2025 to 26 auction. Again, wholesale capacity costs do not flow identically into every household bill. States, utilities, contracts, and time lags all matter. So the accurate answer is frustrating but useful. AI does not automatically raise everyone's electric bill. Rapid data center growth can put upward pressure on regional generation, transmission, and capacity costs when supply cannot expand as quickly, and when the rules allow those risks to be shared with other customers. Regulators are beginning to answer that question with a simple principle. If you reserve an enormous block of power, you should carry more of the risk created by that promise. Ohio approved a special data center tariff with long commitments, minimum monthly billing demand, and provisions to recover build-out costs if a project disappears. Virginia created a separate class for new loads of at least 25 megawatts, with long contracts, minimum charges, and possible collateral. Think of it as reserving an entire hotel for years. If you ask the owner to build a new wing, you cannot cancel the night before opening and leave everyone else in town paying the mortgage. Another fight concerns data centers built beside power plants. If a facility claims it mostly serves itself but still depends on the wider grid for backup, balancing, and reliability, how much should it pay for that grid? FERC's proceedings are trying to match transmission service and cost with the support the large load actually receives. None of these rules makes electricity free. They decide who carries the risk. And that may be the most important design problem in the AI power race. Efficiency matters. Better chips, smarter software, flexible workloads, closed-loop cooling, and well-chosen locations can reduce pressure. More generation and transmission can expand supply. But if the financial rules are weak, efficiency gains can coexist with a very expensive game of someone else will pay. Return to that email at 2 in the morning. The answer on your screen still feels effortless. That is the achievement. Engineers have hidden an extraordinary physical system behind one ordinary button. But hidden is not the same as weightless. Behind the word cloud are chips, buildings, substations, cooling loops, transmission lines, power plants, contracts, and communities. AI is not the only reason that system is growing, but it is accelerating the build-out and concentrating demand in places that have to make real choices. The goal is not to panic over every prompt, nor is it to pretend that digital intelligence floats above the material world. The better question is whether the intelligence is worth the infrastructure, and whether the people making the promise are also carrying the cost and the risk. Your prompt may weigh almost nothing. The system waiting to answer it does not.